let's use the Henderson-Hasselbalch equation to determine the pH of this buffer. This buffer is made of ammonia, which is a weak base, and ammonium chloride, which is a weak acid. Furthermore, the concentration is 0.1 molar ammonia, 0.2 molar ammonium chloride. Now, in order to use the Henderson-Hasselbalch equation, we will need to know the pKa of ammonia, or in this case, ammonium chloride, because this is the acid. So, we might be able to look that up in a table that has pKa values. But if we do find one that has Kb, we'll have to first convert Kb to Ka, and then we can take the negative log and convert that to pKa. Alternatively, you could take the negative log of Kb and then take 14, subtract that, and you'll get the pKa. There's a couple of different ways of determining it. In the table that I looked up, though, it actually has the pKa values tabulated. So, pKa for this is 9.245. And that's the pKa value for the ammonium ion. Again, the chloride is just a spectator ion, so that won't come into play here. So we'll just use our Henderson-Hasselbalch equation. And the pH will equal pKa. Actually, let's write that out real quick. Now, if you remember, this is log of the base form over the acid form. So I'm just going to write what those are in this case. In this case, that's NH3 on top, and it will be NH4 plus on the bottom. So now we'll just plug in the values and calculate what the pH is. 0.1 is our concentration of ammonia, and 0.2 is our concentration of ammonium. And if we simplify this down, we should get a pH of 8.94. Now, there's a couple of ways to make sure that we did this correctly. And let's think about what happened. First, let's compare our answer to the value of our pKa. And you'll notice that our pH is a little bit lower than our pKa value. Does this seem plausible? Well, in order to answer that, let's look back at what we started with. We started with 0.1 molar of our base and 0.2 molar of our acid. And so the fact that this pH is a little lower than our pKa shouldn't surprise us. In fact, that confirms that we probably did this correctly, because acids have lower pH values than bases. And if we have more of the acid form, we should expect that the pH will be lower than our pKa. And indeed it is. This is a good way to check to make sure that I put the acid and the base in the proper spot in the Henderson-Hasselbalch equation. And it's a good idea to keep a little bit of a track of what's happening. If these two values again were equal, then our pH would equal the pKa, and if we had more base than we had acid, then we would expect a pH that was higher than our pKa. Now, as long as there's a good amount of both of these in the solution, we can use this formula. If we get down to where there's no conjugate acid in the solution, this particular formula will no longer work, because we would be dividing by 0. In that case, we would have to use our Kb expression because there's no acid in there. Or conversely, if there were no base in the solution, logarithm of 0 is not a defined value. And so you would need to use the Ka expression and an ice table in order to calculate for that. That is a limitation of the Henderson-Hasselbalch equation that doesn't exist in our Ka or Kb values or expressions. So keep that in mind when you're doing calculations like this. That's another reason why this is often called the buffer equation, because you must have a buffer in order for the equation to work properly. And by having a buffer, I mean that you would have to have some weak base and also weak acid in the solution, and then you'll have a buffer, and in that case this equation will work and we can calculate the pH.